Hello everyone, this is Doug, and in this video I'm going to talk to you about how we can protect alcohols by using ethers and how we can use them as a protecting group. So what I mean by protecting groups, this is something that we may have talked about right when we were doing some Green Fridays and talking about the 12 principles of green chemistry. One of them is to try to avoid using protecting groups, to avoid using derivatization, because it's just, they're extra steps, but sometimes we need to do these extra steps in a synthesis to protect a group from reacting when we don't want it to. So I put down as a definition, it's just a reversible modification to a molecule to, I should say, prevent here, to prevent an unwanted reaction. So let's take a look at this one down here, right? Here I have this molecule, I've got an alkyl halide, I've got this chloride here. It looks like I need to turn it into an alkene. So in my mind, I'm thinking that this is some sort of, right, since I'm going from alkyl halide to an alkene, I'm thinking of some sort of E2. And if I look at this, it looks like it's going off to the right-hand side of the chlorine, the less substituted side, so I need a big bulky base. So I might think like, oh, okay, well, let's do LDA, for example, right, which was the lithium diisopropylamide. So lithium diisopropylamide would be a great example of a big bulky base. Or I could use T-butoxide, but let's use LDA for this one. The problem with adding a strong base to this molecule is that you have this H over here is slightly acidic. So I'll put slightly acidic. Now that's a problem when you add a strong base, right? Is because if it's like T-butoxide, if it's some alkoxide, you're going to at least get like a 50-50 mixture of product where you deprotonate that alcohol. Or if you use something like LDA, it's going to be much higher than that. So if I use LDA, the problem is that LDA is just going to plug off that hydrogen, and it's going to give me an O minus here with attached to the chloride. So dash, 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 dash up, Cl. And now this is negative, right? And then I've remade just the diisopropylamine. So just like this. Right, and if I take a look at my carbons, right, you should always count carbons. I've lost carbons many times before. I lost some on this video earlier, but I've got 6 carbons here. Call these 1, 2, 3, 4, 5, 6. Looks like I've got everything I need. Now the problem with this one, right, is that I was supposed to take off the beta hydrogen on carbon number 6 because I want to do an alkene. I wanted to make an alkene with that LDA, but what's going to happen instead is that all I did was I deprotonated that alcohol, and I have this alkoxide. And we know from first term stuff, right, SN1, SN2 stuff, that when you have an alkoxide and you have a halide, you can do eliminations and you can do substitutions. And there's a really good chance that, for example, you might get something like this, where you do an intramolecular SN2 type reaction, not SN1, SN2. And then I'm going to end up getting a product, 6-membered ring here. I'm just keeping track of all of my carbons. So I'll call this carbon 1, 2, 3, 4, 5, and then there'll be a 6th carbon coming out here. I'd end up making, something like that. And you would probably get some elimination product, and you get all kinds of weird things. The point is you get things that you didn't want, right? You're more likely to get something like this and less likely to get something like this. So the problem here is that I have an alcohol and I'm trying to use a strong base, right? So how do we fix that? So what I would do instead was, right, the whole title of this video is that we're going to use an ether to protect it. And so in this case, what I'm going to do first is I'm going to figure out a way to, let me erase that. I'm going to figure out a way to turn my alcohol into an ether. And you could do the Williamson ether synthesis, or you could add it to an alkene. Either one is going to be fine. It doesn't really matter. Well, actually, let me take that back. It might matter. I'm not going to do the Williamson ether synthesis because I don't want strong bases around, because I don't want to accidentally react with my alkyl chloride here. I'm going to use the alkene route. So what I can do, or a really common example, is to use this 2-methylpropene and a little bit of catalytic acid. Because remember, for example, I'm going to draw this down here. This is a side note. I'll draw this in purple. Recall, I'm just kind of switching it up, but you already know these types of reactions, right? If I had this alkene and I added an R OH and catalytic acid, right? Remember we said, okay, well, your alkene's going to go get your hydrogen. You're going to form your carbocation on the more substituted spot. H is going to go to the less substituted spot. And then your alcohol is going to add on to here. And then a couple steps later, the idea is that you've added your alcohol to that spot, right? It's just an addition to an alkene. You definitely saw it with water. My students saw it with alcohols too, whether or not you remember. And but what we did, right? Notice that what we did was we turned the alcohol here into an ether. And that's what I'm going to do above. The reagents are in a different order, and I know sometimes that feels confusing for you guys, but it's the same stuff, right? I still have an alcohol. All right, so I got this alcohol up here. I'm going to add it to an alkene. That's what I had here, right? Here's my alkene. And so it's fundamentally the same sort of reaction. So I'm just going to take my alcohol, I'm going to take my alkene, I'm going to add them together, and so we're going to get the same sort of product where now I have an ether. So O, all of this is still the same, right? So I have the chloride, only now I have an ether there instead, right? It added to that carbon. And let me just number these carbons for you so that this looks clear-ish. So carbon 1, 2, 3, 4, carbon 1, 2, 3, 4, right? So I had my alcohol attack that alkene. Now, what's nice about this, right, is that now I have an ether, right? This is an ether, and it's protecting the alcohol. And it's protecting it because now I don't have an alcohol anymore. I don't have that acidic hydrogen, so I don't have to worry about it anymore. So I'll say protecting the alcohol. And remember that ethers are really nice because they're resistant to all reagents except acids. So oxidizers, reducers, nucleophiles, they don't react with ethers, just acids do. Strong bases don't react with them. So now I've sort of hidden that alcohol is gone. Now I can go ahead and do that E2 that I wanted to do. Oh, sorry, it looks like I drew that incorrectly. There we go. Actually, I drew it really incorrectly. Let me use my black. Let me fix this for you. Sorry, 1 second here. Up, down, up, down, up, down. We have the Cl out here. So the idea is that now I can go ahead and add my LDA or my t-butoxide or whatever, because now I don't have anything acidic on here except for those beta hydrogens, right? So now I can do my elimination. And I can get the alkene that I wanted, right? There's the alkene that I wanted over here on the end. I did the Hoffman. I got the Hoffman product because I used a big base. But I haven't actually made this product yet, right? I want that alcohol back. I don't want the ether product. I want the alcohol back. And that's where this reversibleness comes into play, right? So it needs to be a reversible modification so that I can bring the alcohol back. And like I was saying earlier, the only thing that ethers are susceptible to is acid. So all you need to do is just add some acid and a little bit of water, and they just unravel. They come back apart. You're going to end up just doing the reverse. You'll get some T-butanol as a side product, and you'll get your alcohol back. And so you're able to make the desired product you wanted, but you had to protect that alcohol and then bring it back. So in terms of green chemistry, right, this is generally not awesome because I'm adding 2 extra steps, the putting the protecting group on, taking the protecting group off, which means it's just wasteful, right? Because you're just wasting carbons. You have to buy the stuff, you have to throw away the garbage. And every time you do a reaction, right, even if the reaction is like 95% yield, your total yield for the whole process goes down and down and down and down. So we want to try to avoid protecting groups whenever we can, which is why we develop new reagents. But still, this is still good for you to know. Let's look at another example. So here we have a reaction where it looks like what I see here is that I have a new piece. It looks like this piece is new. Right, this carbon, if I label these carbons 1, 2, 3, and 4, carbon 1, 2, 3, and 4, looks like I have a new bond here at carbon number 1. I have 2 more carbons, and my carbonyl went down to an alcohol. So this is screaming at me that I must have done a reduction with a Grignard reagent. right? Because I see a new CC bond. So I'm assuming this is some R, Mg, and then some halogen. It can be Cl, it can be Br, whatever. I'll say Br. And so it looks like to me that what we should have here is that step 1 should be this vinyl piece with, again, I'm going to put MgBr. And then step 2 was some sort of acid workup. I'll put ammonium chloride. But, of course, it's not going to be that simple, because if I want to just do that, right, we have to remember that, that these Grignard reagents, right, they're strong bases. So let me write that here in purple. Right, recall that these are very strong bases. So the problem is that I have this acidic hydrogen, right, on the OH. Remember we said that these solvents are usually done in ethers. I didn't write a solvent for this example. I'll write THF, just some ether solvent. Remember that we had to use ethers because we can't use water, we can't use alcohol because they're protic, because they will do an acid-base reaction. So I have to avoid that. So this is another example where I need to hide that alcohol, that OH, so that I can do my reaction on the aldehyde, and then I'll bring the OH back, is the idea. So what I'm going to do instead, right, so this is not going to work, right, this reaction instead, let me write this out. This reaction instead, if I added MgBr, this would attack the H, those electrons would break, and it would give you, unfortunately, this would give me the aldehyde, still here, assuming that we just had one equivalence, and with an O minus, which is not what I was looking for. And then the step 2, the workup step, would just put the H back on the O. So that's not getting me anywhere. So I need to find a different way to do that. Again, this is why we need protecting groups. So what I'm going to do instead, let me redraw this out here. What I'm going to do instead is protect that alcohol. So I'm going to do step 1. Let me erase this here. I'm going to do step 1. I'm going to turn it into an ether. Now, again, how you turn it into an ether is kind of up to you. It doesn't really make that big of a difference. You can do a Williamson ether synthesis method, or you can do the alkene method like I was talking about. Either one is fine. I'll do the alkene method again just because it's a great way to do it. It works really well. So that gives me the aldehyde, but now I have the T-butyl ether again. So now I no longer have that protic hydrogen, right? So I don't need to worry about how strong my Grignard reagent is. So then I'll go ahead and I'll add my Grignard reagent. Now the only thing it can do, right, is attack that carbonyl. So there's no acid-base reaction to occur, so it'll attack the carbonyl to give me that as the next product. These Grignard reagents always have an acid workup. So that's actually going to give me kind of a 2 for here, right? Because if I do an acid and I just make sure that there's water present, I'm going to do 2 things. I'm going to do both. I'm going to protonate. Let me write this up here. I'm going to protonate that O minus. So protonate the alkoxide. And I'm also going to remove the ether. So in the end, I will get that OH back. I just protonated it with my acid workup. And the acid in water is going to react with the ether to give me the alcohols back. And again, remember the side product is T-butanol in this case. If you don't remember what it's like to break up an ether, then I would look back at your chapter, I think it's 11 stuff, was when we talked about the reactions of alcohols and ethers. You just protonate the oxygen, and then it either does SN1 type or SN2 type, et cetera, et cetera. So you might want to review that if this is seeming like totally foreign. But this would be a way that we could use a protecting group, right, to get our product. It takes something that would just be 1 or 2 steps and adds 2 steps to it, which is annoying, but it's a way to protect a functional group, right? To protect a functional group from some unwanted reaction. So let's look at a couple more examples I want to give you. So here's two more examples where you're gonna need to use a protecting group. So I recommend that you pause here, see what you can do. You're gonna have to use an ether as a protecting group. But what's the reaction that we're trying to do here? What's the synthetic reaction we're trying to do? All right, so hopefully you took a crack at this to see where you're at. If I'm looking left to right, to me, the big difference here is that I've got all of this stuff. Let me erase that. I've got all of this business now attached to that carbon right there, right? If I call this carbon 1 and 2, 1 and 2, 1 and 2, right? It looks like I have a new CC bond here. And again, anytime you see a new CC bond and you've reduced a carbonyl, you should be thinking Grignards or organolithium. Again, Grignards is the most common one, so I would go with that. You could use organolithium, but Grignards is probably what you'd used. So I need to add that whole piece that I shaded in green as a Grignard reagent. I'll just throw on MgCl or MgI or MgBr to do that. But again, I noticed that I've got a problem here, which is that alcoholic OH up here. So I need to protect it first. So what I would do is step 1, protect it. Again, you can use whatever ether you want. Let me use a different one. Let me do a different method here just to kind of show you what we're talking about. So if you wanted instead, right, you could go Williamson, where you add like NaO, and step 2, let's use CH3Br, right, so that you get your OCH3, right? So you made a different ether. You made a methyl ether instead of a T-butyl ether. Doesn't really matter. As long as you can take it off in the end, you're fine. And now in this step, I'm going to go ahead and add that big old green piece, right? So now in this step, I'm going to add this complicated alkene-looking thing. And now you could, just as a side note, if you had a really cheap reducing reagent, if you had a cheap Grignard reagent, honestly, you could just add 2 equivalents of this, or like 2.5 equivalents, so that yes, you're going to waste 1 equivalent on doing the acid-base reaction with the phenol, but then the excess, would go ahead and do your reduction for you. So you could add multiple equivalents to get around this particular case. But if your Grignard reagent is expensive or weird, or you made it yourself, you probably don't want to just waste a whole molar equivalent for no reason. So you would go do this protecting group thing anyways. But this looks like a kind of a fancy one, right? I have a very specific arrangement on an alkene that I apparently wanted, so I'm not going to waste it. I'm going to do the protecting group thing. But that's going to give me, that should give me this product. And then again, in this case, I need a second step for the Grignard anyways to put the hydrogen on there, so I need an acid workup anyways. So I'll just go ahead and add this acid workup here for both of them, and it will accomplish 2 things at once. So I got another 2 for here. So I'll just add H3O plus. Really quickly, we'll reprotonate that O and dissolve that ether. There, it's a really, really fast reaction. Now for the second one, it looks like I added this piece here. Right, so I added those 2 carbons. Again, it looks like I need to have, I need to deprotonate that alkyne. And normally I would have to add NaNH2, which is a really strong base, right? NaNH2 is the base that we use to deprotonate those terminal alkynes. But that's so strong that you're going to use it up by deprotonating the oxygen instead, right? Because the OH is more acidic than the alkyne is. So this is another example where you should probably protect it. I'm going to go ahead and use the T-butyl thing again. And again, I could have done a methyl ether, ethyl ether, isopropyl. It really doesn't matter all that much. You just want to make sure that it's something that you can take back off afterwards, which most any ether you can. So now I've protected the alcohol. It's not there anymore. I can go ahead and do my, step 1, add Na, NH2, spaces don't mess with ethers, so we're fine. And then step 2, looks like I added an ethyl piece, so I'll just add an ethyl piece and I'll throw on a good leaving group on there. So let's say I'll make it a tosylate, or you could have picked a bromine or iodine or something like that. So now I've got my alkyne with the 2 extra carbons on it. Just did my SN2. And lastly, I need to remove that hydrogen, so I'll add a nice weak acid and water. Again, you'd use some sort of weak acid here because you don't want to mess with your alkyne by adding a strong acid. So just a little acidity is not going to react with your alkyne. So those are 2 more examples of how to use protecting groups. Go ahead and do some practice. You'll see some great examples in your textbook. Let me know if you have any questions. Thank you. Bye.